All right, so we're thinking about the distance to a line. That's what we're thinking. We're thinking about the distance to a line. And typically today we're dealing with the coordinate plane. So, here, if we look at example 1, it says which point on the line y equals 0. Here's the line y equals 0 if you didn't know. Y equals 0 is that horizontal line that goes through the y-axis at 0. All the y coordinates are 0. Which point on the line y equals 0 is closest to point D up here? Which one's going to be closest? Well, it's going to be the one that needs the most direct path to get there. A direct path is always going to be forming a right angle. Because if not, notice how this is, either way, this is formed with these side lines right here, these side direct paths to point D. They are basically the hypotenuse of these right triangles that are created, because this line is at a right angle. It's able to go straight there, where these are not as close. They're further away. They have to have some slantedness, which is a hypotenuse of that right triangle. So the closest point here would be right there. That is the point 4, 0, and luckily that is one of our options. 2 theorems for us. Through a line and a point not on the line, there exists exactly one perpendicular line to the given line. So it's similar to our parallel postulate from before. Through a line and a point not on the line, there's going to be exactly one perpendicular line to the line. Theorem 42.2 says the perpendicular segment from a point to a line is always going to be the shortest segment from a point on the line. The shortest distance between that point and the line is always going to be the perpendicular segment, always. And that's because what we just realized in the last example, that if we do anything else, a point out here, and we start drawing these horizontal lines, or these diagonal lines, those are going to be hypotenuses, making a right triangle. And we always know the hypotenuse is the longest side, so that would be silly. Here, that distance, that perpendicular segment is what we call the distance to the line. If I were to say, what is the distance from here to New York City, you wouldn't tell me, okay, go around the world and then you'll get to New York City. No, you would tell me the straight path. Type into Google Maps or whatever, it's going to tell you the quickest way to get there. Well, the quickest way for a point to the line is always going to be the perpendicular segment. So that is going to be the distance from a point to the line. Here, find the distance from this point P, which is at 6, 4, to the line y equals 1. Well, y equals 1. The horizontal line going through the y-axis at 1, and we want to know the distance from that point to the line. Well, we know it's going to be perpendicular. Perpendicular to a horizontal line is a vertical line, so that is going to be our perpendicular segment, and there's 1, 2, 3 units between that line and that point. 1, 2, 3 units. That is the distance. 3 units on our coordinate plane. We want to find the distance from that P value, that 0.64 to the line equals 1. X equals 1. It's that vertical line going through the x-axis at 1. There we go. And the distance here, well, the perpendicular to a vertical line is going to be a horizontal line, just like that. How many units is that? 1, 2, 3, 4, 5. 5 units. Find the distance from P, which is 6, 4. Once again, 6, 4. To the line y equals x. Well, y equals x has a y-intercept, is in red. It has a y-intercept at 0 and the slope is 1. If the slope is 1, the perpendicular slope, the opposite reciprocal would be -1. I look over here. If I'm going to draw a line with a slope of -1 going through this point, it's going to go down 1 over 1 towards the line, up 1 over 1 to the left. And I don't want all of this. I just want to know the length of that perpendicular segment right there. Well, let's see how we can do this. Make a little right triangle here. That slanted length would be the hypotenuse. That's 1 unit over, 1 unit up. And so a squared plus b squared equals c squared. 1 squared plus 1 squared equals c squared. That's 2 equals c squared, and so c would equal the square root of 2. The distance between that point and the line is the square root of 2 units. Why round? Just leave it that way. It says given the equation y equals 2x plus 1 and this point s, which is at 3, 2, find the point on the line that is closest to s. So here's our line, y equals 2x plus 1, up 2 over 1, because that is our slope. All right, so there's our line. The point S is at 3, 2. We want to find the point on the line that is closest to S. Well, once again, it's helpful to know the slope of this line. The slope of this line is 2, and I need to know the perpendicular line that goes through this point. So, if I am looking at m being 2, the perpendicular slope would be a -1/2. So starting at my point that I have to go through, I'm going to go down 1 over 2, but I'm going to go closer to the line, so up 1 over 2 to the left. And I can see where I intersect. I intersect that line at the point 1, 3. And so what point is the closest on this line to S? Is the point 1, 3. I do need to find the distance, the shortest distance. It's going to be that perpendicular segment. I can make a little right triangle here. That's 2 units over 1 unit up. Very similar to the last one we did. That's going to be 1 squared plus 2 squared equals c squared, because c, my hypotenuse, is that slanted distance. And so that's 1 plus 4. 5 equals c squared. So c would equal the square root of 5. The distance from S to the line would be the square root of 5 units. That point is at 1, 3 that I'm going to be intersecting that line at. That is the closest point, and that closest point is the square root of 5 units away. So 2 more theorems for us. The perpendicular segment from a point to a plane is the shortest segment from a point to a plane. That should follow very similar to what we just knew about a point to a line. And if 2 lines are parallel, then all points on one line are the same distance to points to the other line. If we have 2 lines and we're told they're parallel, well, if I pick a point on this line, I say, well, how far away is that other line? We would draw a perpendicular segment. If I were to say, well, how far is this line over here? It's always going to be at a perpendicular segment. So it would make sense that these 2 segments are exactly the same, because these 2 lines are the same distance apart. That is part of our understanding of parallel lines.